In this lab, we are going to play with PySpark functionality for machine learning algorithms. First, we will follow a PySpark tutorial in which we will implement logistic regression for a specific dataset. Second, we will change the dataset and the algorithm. And third, we will implement this code in an EMR AWS ambient. We start this lab by creating our EC2 instance, which it is an Amazon Ubuntu. Here, we choose a C5.large size. Once it is running, we change the inbound rules so that it is accessible from the outside. This is to be able to launch the Jupyter Notebook. When the virtual machine is up, we connect to it through SSH. Next, we install Docker. After the installation is done, we start the service. With the Docker service running, we then reestablish the connection via SSH, but this time we add the parameter -l and install the PySpark image. Then, to access the Jupyter Notebook, we type docker ps to get the name of the container, and then we type docker logs plus the name of the container to get the URL for the web interface. Once the Jupyter is open, we then create a notebook to start with the PySpark programming. First, we initiate a Spark context. Now that the Spark context is ready, we can create a collection of data called RDD, Resilient Distributed Dataset. Computation in an RDD is automatically parallelized across the cluster. We can access the first row with take. We can apply a transformation to the data with the lambda function. Here, we return the square of nums. We can also use SQL context. This allows you to connect the engine with the different data sources. Then, we create a list of tuples with the information, build an RDD, convert the tuples, and then create a data frame context. With print schema, the type for each feature is visible. Now that we have a brief idea of how Spark and SQL context work, we will start our machine learning program. First, we start by initializing the SQL context. Then, we can read the CBS file with the SQL context.read.csv. We use infer schema set to true to tell Spark to guess automatically the type of data. By default, it is turned to false. We can see the data with show command. To convert the continuous variable in the right format, we recast the columns. We can use with column to tell Spark which column to operate the transformation. We can select and show the rows with select and the names of the features. We can count the number of occurrences by group using group by and count together. Here, we count the number of rows by education level. To get the summary statistics of the data, we can use describe. It will compute the count, mean, standard deviation, mean, max. To get the summary statistics of only one column, we can add the name of the column inside describe command. We can count the number of people with income below or above 50K by education level using cross-tab operation. We can drop specific columns by using drop operation. We can use filter to apply descriptive statistics in a subset of data. For instance, we can count the number of people above 40-year-old. Finally, we can group data by group and compute statistical operations like the mean. Now, we are starting with the data preprocessing. To add a new feature, we first select the column and then apply the transformation and add it to the data frame. For example, here, H square has been successfully added to the data frame. PySpark has a pipeline API. A pipeline is very convenient to maintain the structure of the data. We push the data into the pipeline. Inside the pipeline, various operations are done. The output is used to feed the algorithm. First of all, we select the string column to index. The input column is the name of the column in the dataset, and the output call is a new name given to the transform column. Next, we feed the data and transform it. Finally, we then can create the new columns based on the group. For instance, if there are 10 groups in the feature, the new matrix will have 10 columns, one of each group. We then can repeat this last step for all categorical features. We then convert the label feature with string indexer and add it to the list stages. Since the input calls of the vector assembler is a list of columns, we can create a new list containing all the new columns. Here we populate the list with encoded categorical features and the continuous features. Finally, we pass all the steps in the vector assembler. Now that all the steps are ready, we push the data into the pipeline. Now, to build a classifier, we need to select the new label and features from the model using map. We create the trained data as a data frame. We split the dataset 80-20 with random split. Then we check some values in the training and test set. We import and implement the logistic regression algorithm. Then we compute the predictions and show some of its values. Next, we proceed to evaluate the model by checking the accuracy and the ROC measure. Finally, we will reduce the time of the computation by tuning the regularization parameter. In this second part, we use the tutorial code as base to change the dataset and the algorithm. The dataset used is called Smartphone-Based Recognition of Human Activities and Postural transitions dataset, and we download it from the EUC machine learning repository. In order to follow this tutorial, we added the headers to the dataset. Here, we follow the steps learned from the tutorial, which were: first, data preprocessing; second, build a data processing pipeline; third, build a classifier; and fourth, train and evaluate the model. The results were a little bit better than the ones obtained with logistic regression for the other dataset. This time, we also computed the F1 score and precision. In the third part, we use Amazon EMR, which allows you to use open source tools such as Apache Spark, coupled with the dynamic scalability of Amazon EC2 and scalable storage of Amazon S3. We can also use Jupyter-based EMR notebooks. First, we go to EMR option in our AWS console and create a new notebook. We choose to create a new cluster that uses 2 instances M5X large. Also, we choose to create an S3 bucket. Once the notebook is open, we choose PySpark to start working on it. We then name our notebook. Next, we need to upload our dataset to the new S3 bucket and grant public access to these files. Then, we can go back to our notebook and start coding. Here, we don't need to initialize the Spark context because it is already initialized. Now, we're copying the code that we have from our last task. The only difference is that we need to change the location of our files. For this, we need to go to the file's location and select the copy path option. We then do the changes in the code. Here, we can see how EMR is distributing the workload within the different instances when this is large. For example, when we are doing some operation to the whole dataset. This might be taking some time, but this becomes convenient when we need to scale our applications or when we need to manage big amounts of data. To finish, we terminate our cluster and delete the S3 bucket.